Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today we'll be simply explaining OSPF cost and the reference bandwidth. In the previous video, we examined how OSPF determines the cost to reach a particular destination. In a topology like this one, we saw that the destination network, when advertised, accumulates the costs of the individual links that must be traversed to reach it. Specifically, the egress interface costs are summed, resulting in this cost value of 3 in the routing table. So far, however, we've seen that each of these interfaces have a cost of 1. But is that always the case? If it were, then OSPF would seem to simply use hop count as the metric, which is quite limiting. But no, that's not the case. The cost measured at each individual interface can differ significantly. Let's see how this is determined. First of all, let me mention that the cost is an integer value represented by a 16-bit number. So it ranges from 1, which is the lowest and best cost, to 65,535, which is the maximum value and represents an unreachable destination. A value of 0 is considered invalid and is unused. By default, the OSPF cost of an interface depends on the interface speed. Now, this needs a bit of explanation. The cost is actually bound to the bandwidth configuration of an interface. By default, this bandwidth value matches the actual interface speed. Bandwidth is a value that you can modify on interfaces, and we'll see that shortly. This bandwidth value doesn't actually change the real speed or throughput of the interface. It's simply a label that is used by OSPF as well as by other processes to function. So what costs are assigned to what interface bandwidths? Well, this table here shows the default cost values for various speeds. Note that for any speed of 100 megabits per second and higher, the cost is 1. Now, this doesn't really make sense. Shouldn't a 40 gigabit per second link have a smaller cost than a 1 gigabit per second link? Well, yes, it should. But remember, this is the default. OSPF was designed way back in the 1980s, and the cost values were standardized in the early 1990s. Back then, 100 megabits per second was the fastest speed around, so it was designated as having a cost of 1, or the best possible cost. That meant that all faster speeds, as they were being developed and used, had the same default cost. Now that's why in our previous videos, we saw a cost of 1 for all of our interfaces, because they were all gigabit Ethernet interfaces. Back then, and even today, for both OSPF version 2 and version 3, 100 megabits per second is considered the reference bandwidth. It is the bandwidth that is assigned a value of 1. Anything faster will have a value of 1, and anything slower will have a larger value based on this equation. Cost equals reference bandwidth divided by link bandwidth. So for a speed of 10 megabits per second, for example, we would have a reference bandwidth of 100 divided by the actual speed of the interface, which is 10, equals 10. So a 10 megabit per second link has a cost of 10. For a T1 link, which is a very old serial type of link with a bandwidth of 1.544 megabits per second, the cost would be 100 divided by 1.544, which equals 64.76. But the value is always floored to the integer, so it's a value of 64. Now we can change the reference bandwidth, and if we have a network with many links at higher speeds, we should use an appropriate reference bandwidth on our OSPF topology. Now let's see what values we'd get if we used a reference bandwidth of 200 gigabits per second. You can see now that we have values that are much more appropriate to the speeds being used. Let's check out how the cost of a 1 gigabit per second link was calculated. We have a reference bandwidth of 200 gigabits per second, divide that by 1 gigabit per second, and we get a cost of 200. It's interesting to see that a link speed of 1.544 megabits per second would be considered unreachable. Any value higher than the maximum would be assigned the 65,535 value, which simply says this is unreachable. Now, it's unlikely that you would have such a diverse set of link speeds where you'd have 200 gigabits per second as well as a 1.5 megabit per second link. But if you do, you would have to make sure that you manually change the cost of that particular link in order to make sure that it will still be used. And we'll see shortly how that's done. Now, the important thing here is that when we change the reference bandwidth, we must ensure that it is consistent across all OSPF routers in our topology. If we don't, then routing havoc will take place with very unpredictable results. Let's take a look at an OSPF topology and see how this reference bandwidth plays its role. Now, I've simplified the topology by removing the alternate path so we can focus on the mechanisms of the reference bandwidth. I've also set up these links here between R4 and R5 to be fast Ethernet links at 100 megabits per second. Let's start by going in and modifying the reference bandwidth on all three routers. We can do that like so. We enter the OSPF configuration mode and apply this command here. The value here is in megabits per second. So this value of 1000 makes the 1 gigabit per second link our new reference bandwidth. Now we apply this to all three routers in our topology. If we had other routers in the same area or in different areas, but part of the same OSPF domain, we would need to do this across all routers. Let's take a look at the resulting routing table of R1. We see that we now have a value of 12. How did we get that value? Well, we have this gigabit Ethernet interface here, which gives us a cost of 1. This fast Ethernet link gives us a cost of 10, and this gigabit Ethernet link gives us a cost of 1 once again. So 1 plus 10 plus 1 gives us a cost of 12. To determine how we get the cost of that fast Ethernet link, we can take the reference bandwidth of 1000 and divide it by 100, which is the speed of our link here, and we get that value of 10. Now, the cost doesn't depend on the actual physical link type. We can adjust how OSPF perceives each link by adjusting the bandwidth value on the interface. Let's do that now. Going into the configuration mode of R4, we enter the fast Ethernet 01 interface configuration mode and configure the bandwidth like so. Bandwidth 50,000. Now the bandwidth command takes values of kilobits per second. So 50,000 is equivalent to 50 megabits per second. Now this hasn't changed the physical speed of the interface, but just the bandwidth label that is used by OSPF. If we issue this command here, we can see the part of the output of the show interface command that tells us the configured bandwidth, which is indeed 50,000 kilobits per second. Now, to be consistent and ensure that routing is performed correctly in both directions, we should apply the same bandwidth value to this interface here on R5 as well. Now, has that affected our OSPF cost in R1 for the destination network? We see here that we have a value of 22 for the cost. Why? Because this link here has a cost of 1000, which is our reference bandwidth, divided by 50, which is the bandwidth that we configured on that fast Ethernet interface, giving us a value of 20. So we have a link cost of 20 here, plus 1 for this link and 1 for this link, giving us a grand total of 22. Now there's one more way you can adjust the cost of an interface, and that's by simply explicitly configuring the cost on the interface itself. This can be done like so. Here on R1, we are assigning a cost of 5 to the gigabit Ethernet 00 interface. This can be done by simply issuing the IP OSPF cost 5 command in the interface configuration mode. This overrides any other bandwidth configuration and reference bandwidth calculations. The result, as you can see from the routing table of R1, is that we have a cost of 26 now. A cost of 1 for this interface, a cost of 20 for this link, and a cost of 5 for this link that we just configured, for a total of 26. For most OSPF implementations, you won't need to change any of these parameters, but there are cases where you need to modify the reference bandwidth to accommodate faster speeds, or the cost of individual links if you want to force traffic in a particular direction. In any case, all of these configurations should be done with care to ensure a consistent configuration across the OSPF domain. For now, I hope you found this video useful, and if you have, I would ask that you consider using the YouTube Super Thanks feature to say thank you and support my effort to simply explain telecom and networking. As I'm always striving to improve my videos, the funds will be used to support better equipment, better quality, better video editing services, and just to produce more useful training content. As always, check out my website where you'll find in-depth courses with labs, quizzes, and exams to test your knowledge and prepare you for certifications, as well as for the real-world networking and telecom industry. And don't forget to subscribe to the channel to get updates to newly published videos. I'm Lazarus at telecomTech. I hope this has been helpful for you, and I'd like to thank you for watching.